Welcome back to the Introduction to Inference, Part 10 of Chapter 14 and 15. We were starting on Example 1, how to do a hypothesis test, and we were talking about how to calculate the p-value. So, we're going to continue with how to calculate the p-value. To test a claim using the p-value approach, the first thing you have to do is get what's called the test statistic. Remember what that is. The test statistic measures the number of standard deviations between the sample mean and the hypothesized mean. So it's just basically getting the z-score, where you take the null hypothesis distribution, the mean and the standard error, and you see where the sample mean is in that distribution. Now we call this z-naught because these are called z-tests. So z is z-score, but we put the subscripted 0, the naught, to let us know that we're talking about the z-score in the null hypothesis distribution. So we calculate just like we would calculate any z-score. You take the sample mean minus the mean of the population divided by the standard deviation of the population. But in this case, our population is the sampling distribution. So not quite the population, it's the sampling distribution of the sample mean for the sample of the size n. So you take your sample mean minus the value in the null hypothesis distribution divided by the standard error, which is sigma divided by the square root of n. Calculate the p-value, the probability that the test statistic would be this extreme or more extreme if the null hypothesis is true. Now, if the null hypothesis is true, the test statistic has a standard normal distribution. So number 3, compare the p-value to a pre-specified level of significance to decide whether to reject or not reject the null hypothesis. That is, to determine if the result is statistically significant. Okay, this is all fine, so how do we calculate this? Well, remember, our calculation will differ for a left tail, a right tail, and a two-tailed test. That is a calculation of the p-value. Once we get the p-value, the criteria for rejection will always be the same. If the p-value is less than your significance level, you reject it, the null hypothesis, but if the p-value is greater than or equal to the significance level, we do not reject the null hypothesis. So let's take a look. How do we calculate it for a right-tailed test? Well, remember what the right-tailed test looks like. Your null hypothesis is mu equals a certain value. The alternative is we think the value has increased. So it's the right-tailed test, so we look into the right tail to see where our sample mean is in the right tail. So the way we calculate the p-value is we say the probability that z is greater than the z-naught we calculate, the test statistic. So remember how we can do that. We can do either by symmetry or by the complement, and on here we show the complement method. For a left-tailed test, that is where the alternative is we think the mean has decreased from the value in the null hypothesis. We're now looking to see if our test statistic is really far out into the left tail. So the way we calculate the p-value, very simply, is just the probability that z is less than z-naught. So we look at z-naught in our table, table A, and the corresponding probability is the p-value. Now the two-tailed test is something different. And here we need to look in both. Remember, we determine our null and alternative hypothesis before we look at our sample. So if we're looking at a two-tailed test, that means that we could have our sample mean be either in the right or left tail. So the way that we find out the p-value is we have to look at the probability in both tail ends. So we would take 2 times the probability that our test statistic is either in the right or left tail. Now, a shortened way to do this is to always make our p-value either positive or negative. So I could do it like this: take 2 times the probability z is greater than whatever the test statistic is, I make it positive, and then I find that probability. Now another way I could do this is say 2 times the probability z is less than negative absolute value of z-naught, where I make sure the test statistic always ends up negative, and then I can just look at the chart and pick off the probability instead of subtracting that probability from 1. But the big difference here is you have to multiply it by 2, because you're going to look at the probability based on your sample to the probability either to the right or left of it, but that sample could have also been in the other tail. So we multiply that probability by 2. As I stated earlier, for all three alternatives, two-tailed, left-tailed, right-tailed, the interpretation will always be the same. Large p-values mean that the observed sample mean is not unusual. That is, it's not unlikely if the null hypothesis is true. So things like a p-value being 0.3, that would be not unusual. So if the p-value if you have a small p-value, that means that the observed sample mean is unusual. It's unlikely in the null hypothesis distribution. So when we have p-values of 0.1, 0.05, 0.01, those are getting kind of small and unlikely that should have occurred, that sample mean should have occurred. That would give us evidence to reject the null hypothesis. But we want to be more specific and have a more quantitative way to say whether we reject or not reject. So what we do is, if the p-value is greater than or equal to our significance level, we do not reject the null hypothesis. However, if the p-value is less than alpha, we're going to reject the null hypothesis. So if we had a significance level of 0.05, a p-value of 0.293 is likely enough compared to the criteria of 0.05. Therefore, we cannot reject the null hypothesis. However, if the p-value was 0.014, it was unlikely and compared to the criteria of 0.05, so the null hypothesis should be rejected. So let's look at that overall structure and then back to example 1. We want to set up the hypotheses, that is the null and alternative hypothesis. Select the level of significance, and like I said, in this class, we'll give you the level of significance. We'll give you alpha. Compute the test statistic. That's how many standard deviations our sample mean is in the null hypothesis sampling distribution. And obtain the p-value. From that p-value, reach a do not reject or reject the null hypothesis decision by comparing that p-value to our significance level alpha. And interpret the decision in terms of the problem. So from our simple random sample of 100, we got a mean height of 69.9 inches. We're going to see how many standard deviations 69.9 inches is in the null hypothesis distribution, where the null hypothesis distribution is the sampling distribution of the sample mean for samples of size 100 with a mean of 69.7 and a standard error of 3 divided by the square root of 100, or 0.3. We're going to test the sociologist's claim that the male business executives are taller on average than the general male population at a 0.05 significance level. That means our alpha is 0.05. Well, here's our null and alternative hypothesis. That should be mu instead of an m. It should be Greek m, which is mu. 69.7 versus the mu being greater than 69.7. So our null hypothesis distribution is the sampling distribution with the mean of 69.7 and a standard error of 0.3. That should say 0.3 right there. Our significance level is 0.05. Calculate the test statistic. So we take our sample mean, which was 69.9, subtract from it the mean of our null hypothesis distribution, which is 69.7, divided by the standard error, which is 3, divided by the square root of 100. So we get a test statistic of 0.67. So to calculate the p-value for a right-tailed test, we say the probability that z is greater than the test statistic we just got. So the p-value, I look in the chart, I find the probability that goes with 0.67, and I subtract that from 1, so I get a p-value of 0.2514. Now, if I look at the p-value and compare it to alpha, my p-value is greater than my alpha. So we do not reject. So how do we state our conclusion in the context of the problem? Well, you answer it. You say at a 0.05 significance level, there is insufficient evidence to support the sociologist's claim that male executives have a greater mean height than adult males in general.